Okay. I just wanted to cover kind of this example that I looked at. This was 20 years ago, but I mentioned the Japanese were interested in building coal gasification and coal liquefaction plants and having supposedly 30-foot diameter pressure vessels that could be 6 or 8 inches thick. And the only way you could do that is weld it in the field. And there's serious problems trying to weld 8-inch thick steel in the field. It was done in battleships in World War II, but typically like a 2-inch plate, if you have some joint and you're doing stick welding, and actually what they do on very heavy joints, for thin joints, you basically just kind of make your 2 plates like this and you just fill them up with different weld passes like this. For a very heavy plate, the X's get wider and wider at the top, and so typically what they'll do is something that might look like this, where they change the shape of the groove and have it narrower, or you're basically cutting off all of this stuff so the thing doesn't get too wide at the top. Anything up to about 1 to 2 inches, you basically weld this way. When you start getting above 2 inches, it pays to start welding inside a groove, because now you're getting to be 2 or 3 inches wide here. And typically, an armor steel, they might have had in a 2-inch plate 200 weld passes. Okay, now that's pretty slow when you're just doing stick electrode. And if you start thinking that the armor steel in battleships was 14 inches thick, no one really, I mean, I guess we could cut up a battleship, we probably have, to find out exactly how many weld passes there. But there got to be thousands of weld passes. I mean, this was an extremely expensive process, okay? And it turns out, what was the thing where the guy blew up the turret down in the Caribbean, the Iowa? And the Navy never really fully repaired that ship. Not that you really needed those types of guns much anymore. But in fact, as I understand it, the shells they were shooting, a couple of times they've shot them in the last 30 years, were all made in World War II. I mean, we don't have a production capacity for that stuff anymore. In fact, we don't have a knowledge of how to weld that type of steel anymore, because you get tremendous residual stresses and things will crack. And they had to go in there and they were peening and doing other things. But when they went to look at repairing the Iowa, there was no one alive anymore who remembered how they did it in World War II, because this was like the early 80s, okay? And so it turns out I was involved with one of the United States' 2 largest forging presses. It's a 50,000-ton press. It's located out here in Worcester. The other one's in Cleveland. They were built by the Air Force after World War II, sometime in the 50s, because the Air Force wanted to forge big, heavy aircraft parts. I mean, in fact, the Air Force was looking at a 100,000-ton press, and they were looking at building it in a mountain in Colorado, because the foundation had to be solid rock. You couldn't afford to build the foundation. This one in Worcester, you go down 6 stories in an elevator just to get to the base of it. And it goes up about 3 or 4 stories above ground, and it's a 50,000-ton press, and they can forge things, almost half the size of this room if they wanted to. It turns out they developed some electron beam welding technology at Grumman and other places. So for some of the aircraft in the mid-60s and 70s, they basically started electron beam welding big sections together, because the forging presses are going to get so expensive. Supposedly the Soviets had a larger forging press, but there's not very many forging presses in the world. And about 15 years ago, they had a crack in one of the I-beams at the one in Worcester. It was a fatigue crack. The thing had been used for 30-some years. And they basically had welded some pads. Now, these pads were not small, about the size of that overhead projector. And they were basically just pads to support it. The beam on the ends had some sloping sides, and they just welded this thing on so it would be horizontal so they could hold it when they were putting it in place. And they never cut these things off, and they left it there, and you had a notch there, and a fatigue crack started. It wasn't necessarily a bad weld, it's just a notch, and this thing got, This thing was 10 feet tall, this I-beam, 10 feet tall, and the web was 10 inches thick. And it's not exactly something you just go out and buy a new one at the local hardware store. So they had to repair it, and there was no one who knew how to weld 10-inch thick steel, because this thing had to be welded and maintain like a 2mm tolerance on the top surface where the press was going to come down. Because there were 6 of these at the bottom, 6 of these beams at the bottom and 6 at the top, basically held the whole press together. So we kind of lost that type of heavy section welding technology. The Japanese wanted to build these huge things, and so I estimated spent a couple $100 million in the early 80s on this large-scale national project, and they had like 10 or 12 of these $2 million electron beam welding machines that were laboratory welders. These weren't the ones you put in the field. The one you might put in the field might be a 10 or $20 million machine. These were just things about the size of this room, that machines that they could weld heavy plate and do research. Well, they learned a lot of things. In fact, I remember I spent a year with the Office of Naval Research in Tokyo in the mid-1980s, and I probably visited half the laboratories that had these machines. And they had finished up the project, just, or they were finishing up the project, and I would go by and I would look at these things, and I noticed all the samples on the floor were dusty, okay? And I'd say, well, have you used this? No, we haven't used it in production. Are you going to? Well, we're just waiting for an order. Well, turns out I finally figured out the 12 problems that they had that they didn't really want to tell me about. Finally, I sat down with a professor from the University of Tokyo one night at dinner, and I said, well, the way I analyze it, I said, no one tells me that this project was a failure, because no one wanted to spend $200 million and declare a failure. But they basically weren't, they had all these problems, and I kind of outlined the problems, and I said, so really, this was a huge investment in this technology, and it really didn't work. And he says, that's right, okay? But no one wanted to admit it. Now, don't look at that as just something native to the Japanese. In the 1960s, the U.S. Navy spent $50 million, which would be the equivalent of about $200 million in the mid-80s, developing HY-130 as a steel for submarine construction. And in the early 1990s, they were talking about using HY-130 to build some submarines. And some of us who knew the actual welding results on HY-130 said, you'll never do it. There were too many problems. But I remember hearing from certain people at NAVC, we can't tell the top brass that we spent $50 million on a project that didn't work. Okay? So this is not, okay, what? You tell them today? They don't tell them. So, it's the old, no one wants to be the bearer of bad news. Anyway, one of the problems they have is lack of long-term beam stability. If you're going to weld one of these things going around at the type of speeds we'll get to down at the bottom, it takes about 30 minutes to go around to make the circumferential weld. Well, it turns out about once every 10 or 15 minutes you'll get a spike in your power supply, and you'll lose your power, and you'll lose your beam, and you'll create a defect because you lose your beam hole, okay? And it was kind of an intermittent thing. It had to do with vapors in the beam. It turns out the vapors coming out of that weld pool are electrostatically attracted right up to the gun. And if you get too much metal vapor up in the gun cavity, you'll get an arc over. And if you lose your beam for more than about 10 or 20 milliseconds, that's the inertial time constant of that liquid pool, and the whole thing will collapse. Your cavity will collapse, and you got to drill a new hole. Well, you've been moving along, and you just produced a defect. So they never did solve the long-term beam stability problem. Inadequate repair method of defects. Well, if I got something that's 8 inches thick, and I have a flaw down here in the middle, I got to dig that whole thing out. And if I dig it out, what am I going to do? Manual repair? I can do a manual repair, but what about my residual stresses when I'm all done? Okay? It'd be horrible to have to repair that. Non-uniform penetration, you saw that in the movie, the spiking that you get. That's kind of inherent in the process. High equipment cost. The research machines were about $2 million a piece, and there were probably a dozen of them in Japan, different research labs. Low utilization factor. If you actually built a real machine for the field, it would probably cost $20 million. And, you know, it might make, you know, 20 welds a year or something. I mean, you know, it's going to be a very low utilization factor. They found that you needed extremely clean steel because you're superheating the steel to temperatures that it never saw in the steel making process. And it turned out not only did you need a low carbon equivalent, which is a measure of your tendency to hydrogen cracking, but you needed extremely low sulfur, phosphorus, and oxygen, because at these higher temperatures you would start generating carbon monoxide gas and you get porosity. So unless you had very, very tightly controlled steel, which the Japanese were capable of making, but it was now going to be not a carbon steel vessel, it was going to be a very special steel vessel, and the costs were going to go up considerably when you're talking about something that's 8 inches thick and 30 feet in diameter. Seam tracking is critical. You can't miss the joint. Okay, 8 inches deep, you know, it's pretty bad, or it doesn't take much to be off. Poor fracture toughness, because this wide heat affected zone, to not miss the joint, and you're 8 inches thick, you probably need a 2 centimeter wide weld. Well, 2 centimeter wide weld means a 2 centimeter wide heat affected zone, which means huge grain growth in the heat affected zone, poor toughness. No adequate non-destructive test technique for something that thick. I mean, typically on an X-ray inspection, and this is part of the rest of the course, that you can measure something when you're doing through X-ray. Something is about that's about 2% of the thickness would show up on the X-ray if you're looking really carefully. Well, when you're talking 8 inches thick, something that's 2% of the thickness gets to be a pretty substantial thickness. Okay, so you can do ultrasonics and stuff, but it doesn't matter what technique you're going to do. Your sensitivity, because you're looking at something big, your sensitivity is going to be generally some fraction of the thickness of what you got, and therefore you've got larger flaws than you'd like to deal with in terms of fracture toughness. In addition, heavy plate, if you go look at the tightest ASTM standard for heavy plate right now, to buy it from a steel mill, it says if you do ultrasonic inspection of this plate, the largest permissible defect must fit within a, I can't remember if it's a 6-inch or 12-inch diameter circle. Okay, well, wait a second. It's a pretty good sized flaw in the middle of that plate, right? But they can sell, I mean, that's the best quality you can get. That's the highest standard if you're looking at very heavy plate. Big heavy plate came from a great big casting. Great big castings have great big flaws from the solidification pores and defects and stuff. And they don't have a lot of mechanical working to squeeze the flaws together and weld them together, right? So it turns out you have a problem with quality of plate and other things. Weld in crater defects. This spiking phenomena gets worse and worse if you're doing a partial penetration weld. Well, when you're going all the way around the seam, you're doing a full penetration weld until you get to tie it in at the end of the circular weld. Now you're welding partial penetration, and you always produce defects. So in crater defects was a problem. You need a large vacuum or a local vacuum, adds to the cost. And it turns out they found that as they went to thicker and thicker plate, the processing parameters that you could use narrowed in terms of voltage, current, travel speed, and whatnot. On a 20 millimeter plate or an 80 millimeter plate, so 20 millimeters is what, 4 inches, and this is 12 inches or so, something like that. All right. No, is that right? No, this is 8 inches. No, 2 centimeters. So this is 2 centimeters and 8 centimeters. So 8 centimeters is like 4-inch plate. This is relatively thin. This is only 4-inch thick plate, or 3 or 4-inch plate. Anyway, you could have almost a factor 2 in travel speed and a 1/3 variation in your power per centimeter of weld, and still get a good weld. But when you go to the thicker plate, you find that you can only tolerate, instead of about 75% variation, you can only tolerate a 50% variation in travel speed and only a 10% variation. And you try to go to 120 millimeter plate, which was their goal, and that processing window shrinks down to nothing. Okay, so when you try to do a great big project, this was done by some some manager who said, wow, this would be some way to do something. They really didn't understand the process and all the problems. They spent a lot of money over a very short period of time. That's always the case when you try to do all your work over a very short period of time. You get yourself in trouble, okay? Costs go up by a tremendous amount because you're trying to do everything in parallel, or you skip things and then you find that it comes back to bite you later, okay? So that's basically just project management. So that's just kind of a case study. I could talk about more recent case studies than that, but we were talking about electron beam. One of the most recent ones that I dealt with was a couple of years ago was the X-33 space plane, where NASA said we want to build this space plane in 33 months from start to finish. And they went, and I think I told you about some of that, the adhesive bonding problems, okay? And they ended up with junk. It's only $1.3 billion, right? That wasn't just, the tanks were only 100 million. The 2 tanks that failed were only 100 million of that. Okay. Then you requested kind of a special topic of underwater welding. So underwater welding comes in two flavors, wet or dry. You actually can strike an arc underneath water and the arc works just fine. You have to be careful a little bit with the equipment that you don't electrocute yourself in the water, that the proper things are grounded and you're not at a high potential because you're going to be in the water. But in fact, it's not that hard to do. And people do weld underwater. It turns out the first thing you need to know, and I think I mentioned this before, the arc is not stable above 30 atmospheres. It doesn't matter whether you're underwater or whether you just do this in a chamber with high pressure gas. If the external environment of that arc gets above about 400 psi, the arc goes unstable. And that's partly because arcs are kind of a weird beast. If you cool the outside surface of an arc, it actually gets hotter on the inside. Because remember, the arc has to carry the current, and if you cool the outside surface, you are basically shrinking the diameter of the arc, but in order to carry the current, it has to generate enough electrons, which means the plasma has to get hotter. So initially, as you squeeze an arc, the arc constricts, and the percent ionization in the arc increases, and the whole thing gets hotter, and you have stronger plasma jets, which is the next thing. But if you keep on doing that above about 30 atmospheres, you eventually get into places where if you have any type of perturbation, that high pressure basically swamps out the arc and just shoves the gas away, okay? The convection currents on the outside become unstable. So it becomes unstable whether you're in a gas or whether you're surrounded by water. But you can strike an arc underwater because essentially you're generating this gas, and the gas is pushing the water back. And you can do it. You can do it to several hundred feet wet. Now, if you actually take 30 atmospheres, that says you can only go down to about 1,000 feet, because if it's 440 feet or 440 psi and it's 0.44 pounds per foot, that's the reason I took 440, right? I divide, and I get 1,000 feet. Well, whether I'm doing it wet or dry, if I wanted to weld at more than 1,000 feet, you can do it, but you have to take a chamber with you and pump out the chamber to a lower pressure. You can't do it at the barometric pressure down there. Okay, so you have to build a chamber around it. If you're going to build a chamber, you might as well do it dry, because there's other problems with doing it wet. Now, I know you guys are interested in underwater welding, not at 1,000 feet, but about 30 feet, right? Or something like that. Okay? How to repair that ship when you get a hole in it, for whatever reason, right? And so it can be done. The problem is, well, the welding is different, and so it takes some practice. The arc gets constricted by the pressure, gives you stronger plasma jets. Stronger plasma jets means if the welder doesn't have some practice, some experience in that, then, well, first of all, if they're doing it wet, you're welding through bubbles, right? Not only do you have to have goggles on to keep from burning your eyes, but you're welding through bubbles, and you can't really see exactly what you're doing, okay? So it's sort of like a blind man welding. You can't really see the puddle with the same sort of clarity that you can see ordinarily. And all the smoke is getting into the water and clouding up the water. Sometimes the water that you're welding in is not very clear to begin with, right? So you get a constricted arc, you get stronger plasma jets. The stronger plasma jets cause greater gouging of the weld pool. Typically, you can weld up to 200, 250 amps before the plasma jets get so strong they start digging metal out of that weld pool. But in wet welding, depending on the depth you're going to, you may only be able to get to 125, 150 amps before that constricted arc gives you stronger plasma jets to start essentially digging holes in the metal rather than just kind of melting the metal and leaving a nice simple little bead. Plus the stuff quenches very quickly if it's wet welding, and therefore you get these terrible ropey looking beads. The welder can't see what they're doing very well. The plasma jet is different. Relatively few of these welders really have experience welding underwater. I mean, frankly, I doubt that the Navy does it, but you really ought to require that 1 or 2 people on board ship, you know, one of the chiefs, you know, or whatever, go to a 2-week school and just weld underwater, okay? Okay, they don't do that. And yeah, you're lucky if they even know how to weld, and they just send them down there and say, make a wet weld. Well, you know, it's kind of like putting somebody on the top level of a video game. First time they have to make a critical weld. You know, there's no training. I mean, if you really want, you think about all the other spares you have on the ship, okay, to be able to repair things, you might want to have a spare personnel who actually has some knowledge of what they're doing. Either that or fly somebody in, okay, which in some cases they do. Well, they do sometimes, but even so, you don't always have that luxury, right? So anyway, the weld metal chemistry changes. So you're interested in temporary welds, I understand that. But it turns out the oil companies are actually interested in repairing rigs that are going to be out there. They don't want to take those rigs off station. Those rigs can be costing you $1 million a day. Well, not $1 million a day. The rental, well, actually they cost you to operate and everything else, and the profit coming from them could easily be $1 million a day. But a good jack-up rig, good-sized jack-up rig, can rent for 75 or 100 million a year, so that's a third of $1 million a day just for the rental costs. Okay, now the rental costs include some of the operating people too, but nonetheless, the weld metal chemistry changes because I got a higher pressure. And in a steel weld, which is what you're going to be welding most of the time, it turns out higher pressure means that I got more CO gas. And the CO gas has an exchange reaction with the weld pool, with the carbon in the weld pool, and you're going to get more recovery of carbon. It turns out if you look at typical welding or weld metals, you've got to worry about carbon, manganese, oxygen, silicon. As it is, we formulate special electrodes with different amounts of manganese and silicon just if we're welding with argon shielding when we're doing gas metal arc, or whether we're welding with 100% CO2. In fact, I remember Professor Blue brought me this fatigue failure. He was a fracture expert here. And he had this brittle, fairly brittle, there's a fatigue crack from a bridge, and it was a weld, and the hardness was terrible. That's one of the reasons they had the fatigue crack, and it was brittle. And he had done the chemical analysis on the weld metal, and he had like 1% silicon and 2% manganese. He says, how did we ever get a weld metal like this? It wasn't because it was wet welded. It was because they used a 100% argon, 100% CO2 welding wire, and they probably used argon shielding as the shielding gas. Ordinarily, you have to have wires with like 2.5% manganese and 1% silicon with 100% CO2 because the 100% CO2 is going to burn off a lot of manganese and silicon during the welding process. You're going to lose those alloying elements. So you have to put extra into the wire, okay? And if you're going to use 100% CO2, which is more oxidizing, you've got to use a richer chemistry wire. It turns out if you then use that with an argon shielding, and they'll sell you a different wire for argon shielding. Okay, now they also try to always sell you wires that'll do both, right? So they're not optimized for either. Okay, they're basically deficient in both respects. And I had a situation in a building down here in Boston, a big high-rise there, building a year ago or a year and a half ago, and that was one of the things the company that made the welding electrodes recommended a particular wire. The guys were using 100% argon. This was a wire that could be also used with 100% CO2, and it ended up getting to be too hard. Okay, and they had some cracking. And those were welds. This was kind of the critical structure. This was a building that had kind of something. It had like 30 floors going up, and this was the piece that kind of didn't go straight up from the bottom. You know, kind of like the status center. You know, no one knows how to do a square rectangle shape or something. Basically, the building came up, and then as it got above the other buildings around it, it kind of flared out. And these were the knuckles that basically were the stress points for the rest of the building going up. And so these were like 6 or 8 inch thick welds. And the guy actually had been a welder at Electric Boat. He's one of the best welders I've ever seen. Beautiful welds, just had cracks in them. And it wasn't his fault. It was because they had the wrong chemistry of the weld metal. So the weld metal chemistry changes. You really need electrodes that are formulated for underwater welding. And there are people who make them. The Soviets, who never worried about economics, developed some great underwater welding electrodes. You don't find them in the United States. We just take things that were developed for something else and we just use them. Okay? So you end up with a high hardness, you know, and then you're going to weld it in a wet environment, so you got plenty of hydrogen. Your carbon equivalent goes through the roof, and you wonder why the welds crack. Well, the welder can't see. The whole process is unstable, basically becomes less stable. The chemistry goes bad on you, and you quench it to make it as bad as you possibly can. I mean, you can't design a system that's much worse. Okay? You actually could design this one to be better if they actually used special electrodes and the people had proper training. And the last thing is barge cost, which you don't have to worry about, but in the commercial world, if you go down and you don't want to take an offshore platform off station because it's making $500,000 or $1 million a day for you on station, and if you take it off station, it's probably going to be 1 to 2 months. It's just like putting a ship in dry dock, you know. I mean, it's not all that different, right? You're talking about millions of dollars a day or $1 million a day, whatever. Use a number, but it's that order of magnitude. It's not $100,000 a day, and it's not 10 million. Well, it could be 10 million in a great big thing if you really got a very productive platform. But order of magnitude, you're talking $500,000 to $1 million a day, and big lay barges or production barges to do it on site get expensive, and if you're doing it down very deep in these offshore platforms and stuff, where you're down 400 or 500 feet and you have to have chambers, you're going to do dry welding, you're going to repair this thing. It can take 2 days just for the diver to get, you know, pressurized and depressurized before, you know. So you're going to get down there and do half an hour's work, but it takes you a week's time. And the barge is going to end up costing you $500,000 a day. So these get to be pretty pricey welds. Okay, these are your multi-million-dollar welds. They may not be very big, but the alternative is to cost you $50 to $100 million to take the whole thing off station and go repair it in the shipyard. So it gets to be a very, very interesting system. And in fact, I should have kept this thing a month ago or 3 weeks ago. I actually saw a plot somewhere of all the piping, underwater oil pipe in the Gulf of Mexico. And it's just all over. I mean, it just looks like someone spilled spaghetti on the Gulf, right? The thing's full. Yeah, it's just incredible, all the piping they're doing from the offshore oil rigs. Well, those lay barges, if they're costing you $500,000 a day, and they got to lay the pipe, they're not welding underwater in that case, but you're talking about barges at $500,000 a day, welding pipe together, and one of the problems is you can't you can't double joint the pipe in most cases, or you might double joint the pipe, but you have a hard time getting to triple joint the pipe. There's two ways to lay the pipe. There's S-lay and J-lay. And S-lay, here's your ship, and you basically have the pipe coming off and going into the water and forms a big S. In J-lay, here's your ship, and the pipe, well, actually you'll have a hole in the ship, so the pipe will come down and like that and forms a J, right? So you're welding the pipe vertically, you know, the pipe's standing up vertically, and you're making the weld this way. Here you're making the weld going around when the pipe's laying horizontal rather than vertical. So S-lay is horizontal welding, or it's actually it's the 5G position, which is basically going around from 12 o'clock down to 6 with the pipe running horizontal, and J is with the pipe running vertical. Well, in this one you might be able to double joint the pipe, and it depends. This typically is heavier pipe than S-lay because you have to have a certain more flexibility. You got two inflection points here, or you have one inflection point. So you might double joint the pipe. Typically the pipe comes in 40-foot lengths, so maybe you have 80-foot lengths that you have to weld here. Here you got to weld every 40 feet because you don't want this thing going 8 stories up in the air, right? And you start getting into ship stability and other problems when you got this heavy piece of steel as a mast up in the air. And so people will spend fortunes to weld faster in these positions, okay? Because it's not the cost of welding, it's the cost of renting that pipe and the tugs and everything else that's going on around there. I remember there was one story when they were laying pipe in the North Sea. It was a few years ago. But the barge has to be anchored has 6 anchors to hold the pipe laying barge. And the pipe, when I say barge, it's not a small barge, it's actually a small ship, okay? But it has to have six anchors to keep it steady, and these things are dynamic anchors, you know, lines that are kind of keeping it positioned and not moving too much. And they had a problem that one of the capstans basically broke. Well, that was okay, they still had 5, and then another one broke. And at that point, they had to come in because the insurance policy said you couldn't be out there with less than 4 anchors working, right? You probably could have done it theoretically with 3, but the insurance policy says you had to have at least 4. So they had to come back in. And it turns out it was the keyways had sharp cuts in them for the keyways on the capstans. I mean, it's such a, you know, we've known that for how many, 50 years? But some guy designed this thing and he didn't know it, okay? And it cost tens of millions of dollars to come in and repair that. Okay, any questions on, I mean, that's kind of the things you have to worry about in underwater welding and why it is such a pain. It's basically because it's not done often enough that anyone has ever bothered to spend a lot of time trying to fix it. Actually, I brought this, I passed this around before, and just, I don't think I mentioned, this was plasma cut. And actually, most of the plasma cutting is done underwater. It's a plasma arc, and it's run underwater. And in fact, you get a very small heat affected zone on this thing. It's only about 1 millimeter rather than a couple of millimeters, which is what you'd expect for steel of this thickness, because the whole thing is submerged underwater. And the reason they do that is not that you can't plasma cut above water, but it's all environmental reasons. If you do plasma cutting on this, you will generate smoke that just looks terrible, okay? It's not necessarily that harmful. Well, actually, this is stainless steel, so it might be. It's got chromium in it. But for the carbon steel, which they cut that way too, it's not that it's necessarily so harmful, but it's better. Plasma cutting has taken over from oxyacetylene cutting because you can't do oxyacetylene cutting underwater. Plasma cutting you can do underwater. It can be faster and it can be a smoother cut, but it's much, much more expensive equipment. But the real reason it's been taken over from oxyacetylene on carbon steel is because the environmental reasons. You catch all your fume in the water, and you just basically filter the water. It's just iron oxide, which is not really toxic. So you filter your water, and you end up with a nice clean cutting operation. So people cut underwater in most cases. In this case, it's underwater arcs, okay? And another proof that we're using more and more underwater arcs, but primarily for cutting and for environmental reasons more than anything else. Okay, any other questions, concerns? Okay, you can shut that off. We don't need